We're now going to look at slightly more complicated examples of probability where you've got multiple events. So at the end of the lecture you should be able to calculate the probabilities for multiple events using the addition and multiplication rule. And that also means that you need to understand the terms mutually exclusive and independent. So to calculate the probability of multiple events that occur together, we usually label the events A and B to be particularly exciting. So the additional rule tells you how to calculate the probability of either event A or event B happening. So just remember that this is or. So in that case, you want to add up the areas for the two different events. But this is only true if the two events A and B are mutually exclusive. So mutually exclusive means that the two things can't happen together. Now with a die, that's simple. You can't have it land on two different faces together. It has to land to show one particular face. So the chances of 1 or 5 turning up is you combine together the area for 1 and 5. So you end up with double that particular area. Now, events are mutually exclusive if you draw them as a Venn diagram if they don't overlap with each other. So the probability of event A or event B equals the probability of A plus the probability of B. So the probability of rolling a 1 or a 5 equals 1/6 plus 1/6 is 2/6, which is a third. Mutually exclusive events don't overlap within the Venn diagram, and they cannot both happen. Even numbers and odd numbers, they can't both happen. Now, if I want to figure out the probability of getting a 3 or an even number, then I add up the probability of all the even numbers, which is 1/2, plus the probability of getting a 3, which is 1/6, so that's 4/6. Now, a counterexample is 4 and an even number. These are not mutually exclusive. 4 is a member of the set of even numbers, so they would overlap with each other. And they're not mutually exclusive. If you have mutually exclusive events, then you have to take away the area where they both occur from adding the two areas together. Other examples of not mutually exclusive events is rolling an even number and a 6, drawing a card and it's a 7, because the 7 of hearts is not mutually exclusive. It fits in both of those different categories. So as I said, in general, if you're not going to take into account their mutual exclusivity, what you need to do to calculate the probability of event A happening or B happening is add the probability of A to the probability of B and then subtract from that the probability of A and B both happening together. Now, the multiplication rule describes the probability of A and B occurring. That A and B both occurred at the same time. Now, if I roll my die once and get a 6, and I roll my die again and get a 6, then the probability of getting 2 6s is the probability of 6 on that first roll multiplied by the probability of 6 on that second roll. So it's 1/36. Now the problem is that die are not a great example in this particular case. As imagine what's the probability of getting a 6 followed by a 1? So the probability of a 6 on that first die is 1 over 6. Probability of a 1 on the second die is 1 over 6. So the probability of having a 6 followed by a 1 is still 1 6 times 1 6 is 1 over 36. And this confuses people. People get confused that the probability of two identical events, two 6s, is still the same probability as a 6 followed by a 1, or 6 followed by a 2, or a 3, or a 4. All of them are equally likely, because you're specifying the number on both of the different die. If the order doesn't matter, then the probability is different. So the probability of getting two 6s there's only one way of doing it if I roll 2 die. But the probability of getting a 6 and a 1 doesn't have just one chance of doing it. I could have the 1 first and the 6 second, or the 6 first and the 1 second. So those probabilities are different when you don't need to take into account order. Now, one thing you need to consider when you're doing your probabilities is, are the two events independent of each other? So when I rolled the die the first time, and it's 1 over 6, does that change the chance of me rolling a 6 the second time? No, it's still 1 over 6. If I have a bag full of tokens, so it has 6 red tokens and 6 blue tokens, and the first time I take out a red token, then the probability both of the red and the blue tokens for taking a second token out of the bag, their probabilities have changed, because I've no longer got 12 tokens, I've only got 11, and I've got one less blue token as well. If I picked a blue token the first time I pulled one out. So in that case, the probabilities are not independent of each other. Now in biology, you can use these probabilities of independence when calculating things to do with genetics. So unfortunately, this was a catastrophic miscalculation of the probability of cot death by Professor Roy Meadows. So the calculation that they'd originally made was there's a 1 in 4,000 chance of a child dying from sudden infant death or from cot death. So he calculated the probability of 2 children within the same family dying from cot death would be 1 over 4,000 multiplied by 1 over 4,000. That is a very small number. So it's 1 over 16 million. The only problem with this is, are the two events really independent? You've got a child from the same parent living in the same house in the same conditions. So in this case, genetics is going to play a factor, as are environmental conditions, as is the way that you're bringing up the children, whether you've read Dr. Spock's book on putting them face down. But because he gave evidence in cases where they'd had multiple cot deaths from parents, he persuaded a jury to convict a mother of murdering her children because they had multiple cot deaths. Eventually, the case was overturned and his evidence was questioned by the Royal Statistical Society, but unfortunately the damage had been done to the family and particularly to the mother, who had alcoholism and stress-related illness and died younger than she would have without those tragic events. Another way of looking at probability and flipping coins multiple times is to construct a probability tree. So imagine flipping a coin twice. The first flip could be heads or tails, so the probability is half. The second flip can be heads or tails. So what's the probability of flipping a coin and getting a head followed by another head? So head first and head seconds. So you've got probability of A and B both being heads. So you multiply the two together. Half times a half equals a quarter. But if I draw it up as the probability tree, this is what it looks like. So you've got your flip of your coin. So you go half probability going to head, half probability going to tail. Then for the second flip, you've got head A, tail B, head C, tail D. So the result that I want is a head followed by head, which is the path that leads to A. All of the other pathways don't lead to A. So then it's one out of those 4 possible pathways, so the probability of getting head followed by head is 1/4. Some people prefer to draw probability as trees. Some people prefer to calculate it by other methods. Pick the method that works for you.